Hello everyone and welcome back to PC Retro Programmer. In the previous video we tried to speed up some code that we've been developing for drawing ellipses. It all started with wanting to draw circles. This was many videos ago, and we noticed that our circles were squashed when they were drawn on the screen. And this is because the pixels are not square. They're actually a little higher than they are wide in the ratio of 6:5. So we had to actually draw an ellipse in the ratio of 6:5 to compensate for this. And we've been gradually trying to get faster and faster code for this. First of all, we reflected the ellipse about the horizontal axis, and this made a big speed up. And we thought perhaps we can get another speed up by reflecting in the vertical axis. And that's what we did in the previous video, and this is where we're at with it. This is a circle, so it's actually an ellipse in the ratio of 6:5 to compensate for those non-square pixels. And it runs pretty well, but it was only about 3% faster than the version where we didn't reflect in the vertical axis. So it seems like we're running out of ideas here to speed things up. But that's actually not the case. In today's video, we're going to come full circle, if you'll excuse the pun. There is a way to draw circles even faster, and by circles here I still mean ones that are compensating for the non-square pixels, so really ellipses in the ratio of 6:5. You might wonder, well, how on earth can we possibly go faster? We've pulled every trick in the book, haven't we? Well, that's what we're going to look at in today's video. Now, the trick that we're going to use in today's video relates to the ellipse drawing routine itself, which is over on the left here. And I've already gone through this, and I've removed the code for actually drawing pixels and for computing the coordinates x and y of the pixels that we're drawing. And everything that's left here just relates to the decisions that we're making about those pixels. So the initial constants that we start off with, the three variables, dx, dy, and d, and all of the updates to those variables, sometimes involving our constants, and the decisions that we make using those variables. So it's just the pixel drawing code that's actually been removed here. And what we're going to do is we're going to write a special version of this that just works for circles. Now, for us, a circle is an ellipse in the ratio of 6:5. In other words, our horizontal radius r is 6 times something, and our vertical radius is 5 times something, so that they're in the ratio of 6:5. So I'm actually going to go through and make that change in this algorithm. I'm going to replace r with 6 times t and s with 5 times t throughout. So this is what it looks like here. Initially we had c equals s squared here, and now we're saying that s is going to be 5 times t, and when you square 5t you get 25t squared. And similarly I went through and changed all these other values. The only exception is dx here. I left one r in place, and the reason for that is that the way I've written everything now, all of these values are multiplied by this t squared factor. And this is really interesting because now we ask the question, well, what would happen if we got rid of all those t squareds? And I'll explain why we might want to do that in a moment, but let's just think about it in terms of some of this code here. So imagine we scaled dx and c down by t squared. Well, the result would be scaled down by t squared. And actually the same thing happens for every other thing that we do in here. Even weird comparisons like this, what this is really doing is dividing dx by 2 and rounding down to the nearest integer. Even this will still work. And you can see that if you think about what this is actually doing, it's making a decision based on a particular cutoff. And that precise cutoff is when d equals 2 times dx. But if d and dx are both scaled down by the same amount, this comparison would still be exactly the same. And so everything that we do in our code doesn't need to be changed at all. All we need to do is change these initial values just by dividing through by this t squared. Now I'm going to go through and do that in a moment, and in addition to that I'm just going to replace all of these 2a's and c's that occur in my code here with the actual values. See, once I get rid of the t-squareds here, I'm just going to be left with c equals 25 and a equals 36. So the c's will just become 25s, and the 2a's will just become 2 times 36 will be 72s. So this is the result here, and that really looks a lot simpler. So here's our original variables as we set them up, and I've gone through and just replaced all those constants. Now it turns out that there's one major benefit from doing all of this. All of the values that we're using now are much smaller. And remember that one of the problems we had with the ellipse drawing code is that the values were getting too large for a 16-bit CPU register. In fact, we actually had to use 24-bit values for each of our 3 variables here. So that meant that instead of using 16-bit registers for these, we had to use 1.5 registers for each of them. But now with this version of the algorithm, the largest value this code actually sees is basically this one here, this dx value, which is 50 times the radius of the circle. Now, if you think about a circle that actually fits on the screen, it can't be bigger in the vertical direction than 200 pixels because that's how high the screen is. So the radius in the vertical direction would be 100. And of course, we have to scale everything by 6/5 to get the radius in the horizontal direction, and that means that this r value here won't exceed 120. And that means that dx won't be any bigger than 6,000. Now that's really cool because that fits in a 16-bit register, and so basically all of our 3 variables fit in a 16-bit register with this version of the code. Now that's going to save us a total of 1.5 CPU registers. And that's really cool because in the previous video, one of the problems we had is that in order to do our reflection about the vertical axis, we had to add an additional 1.5 registers worth of memory variables. But now we've just freed up 1.5 registers in the CPU, and so we'll be able to do that trick without needing the extra memory variables. In addition to that, all our 24-bit comparisons will now just be ordinary 16-bit comparisons. You can see that our constants are already in our code, so we don't need to do any self-modifying code to update those. And there are lots of other savings as well. So let's take a look at the code and see just how much better this is now. Well, this is our new code. It's in circle5.asm, simply because that's what we're up to. But it's actually derived from ellipse6.asm, which is the code we had in the previous video. And if you want to find this code, it's at the link in the description. Now, the first thing I did is to get rid of the memory variables that I introduced in the previous video. They're gone now, and that's because, as I explained, we're going to use CPU registers for those values instead. Now, I did make a very small change here. I decided that I want the dx variable to be in the dx register, just because it's easier to remember. I went through and made that change everywhere, and that means that the registers that are free now are the bx register and the cl register. So you can see that what I previously had in those memory variables, I now have in registers. The left offset word is in the bx register, and the left mask byte is in the CL register. Now, another change I made here is I got rid of S. If you look at our algorithm on the left there, S doesn't appear anywhere anymore. This is a circle, it only has one radius, and in fact our algorithm only needs the horizontal radius R, and so I got rid of the S argument to this function, and everywhere that it's called I no longer supply an S. And of course this is called CGA circle now instead of CGA ellipse. But those are all very minor changes. Let me scroll down to the first place where I actually found a speed up, and it's something that I actually could have done for the ellipse code as well, and I'll probably have to go back and make that change now that I've spotted this. Previously, after this shift left of CL by 1, which effectively multiplies it by 2, I had two increments. In other words, I was adding 1 twice. And this is really silly because I realized that multiplication by 2 then add 2 is the same as add 1 then multiply by 2. So what I did is I left the multiply by 2 here and I moved the add 1 up to here. And this has another knock-on effect. Because I'm now doing this increment before I do this AND instruction here, it means that we never end up with a value of 4. And remember, that gets multiplied by 2 down here, so we never end up with a rotate by 8 bits here. And remember that the rotate instructions, the amount of time they take depends on how many bits you're shifting by. So instead of rotating by 8 bits here, I would now only be rotating by 0 bits. So that's going to take less time in that specific case. So that's another little saving that I got for free here. Now, as I said, I could have done this in the ellipse code. This has nothing to do with the savings that we've made for this circle code, but I thought I'd point it out anyway. So now there's a little bit more code for setting up the offsets, and I won't go through that because it's pretty much exactly the same. It just doesn't use the memory variables anymore. And we get down to the code for computing our constants and variables. Now, all the code for computing the constants is gone. Remember we were using self-modifying code for that previously? Well, we don't need any of that anymore because the constants can actually just be put directly into the code since they are really constant now. They don't depend on the parameters at all. And the variables, well, I have to set dx to 50 times the radius. I don't use a mul instruction here because I'm multiplying by a constant now, and this is always faster to do manually, just using some shifts and adds. So that's what I do here. And you can see that all the mul instructions that I had in all of this setup code, they're all gone now. So this is going to be way faster. And there's also just this dy value which I set to 36. Now, as I said, all of this is just in our setup code, so it's only run once and it's not going to make a huge difference. Let's jump down to the first place where we'll actually get a really noticeable difference because it's in our main loop. So the first 2 pixels that we draw, that's exactly the same as before. The next 2 pixels, of course, I have to use the CL register instead of the memory variable now. And what I've gotten rid of here is all of that ugly code that I had for swapping out values with the memory variables, which we know was really slow. So that's a big saving here already. But we get much bigger savings. We'll scroll down to here. This is the first update to one of our variables that we do. And you can see here that to add dy to the d variable, it's just a single instruction now. Previously this was a 24-bit addition, which was 2 instructions. So there's a big saving there. And similarly, this would have been a 24-bit addition, and now we're just adding a single constant value to the BP register. This is going to be faster as well. And I had to make another little change here. You can see that when I'm drawing pixels now, if I go up to the pixel drawing code, I basically have to use the BX register for the offset on the left-hand side within our ES segment. That's our CGA video RAM segment. And this means that I can't use the STOSB instruction because that only works with the DI register. So instead of STOSB, I have to use a move instruction here. Now that's all fine, it's just that STOSB automatically increments DI, and we don't do that here. So that means that down here, instead of subtracting 8113 from DI, I have to subtract 8112, just because I'm not using STOSB. So that's just a little change that I had to make, but otherwise everything's pretty straightforward. Now I won't go through all the changes that I made here. A lot of them are exactly the same sort of thing. You can see that all of these are now 16-bit subtractions. The other big change came for the comparisons. Now remember that those were previously 24-bit comparisons, and they're now just 16-bit comparisons, which we can do much more simply using just the compare instruction and a conditional jump. So this is going to be a very big saving. All of those jumps that we had to do those 24-bit comparisons were really expensive. A little bit further down, there is another comparison, and you can see it here. Basically, again, it's now a 16-bit comparison, and I now jump up to this instruction here. Now I've moved this around a little bit. In the previous video, I think I had that jump in between these two here, and this was a bad idea because it meant that I was doing one more jump that I needed to, and by moving it up to here, I actually save just a little bit more time with all of these jumps. Now I actually could make that change in the previous code as well. So again, I should go back and modify the ellipse code, but that's a relatively small change compared to the fact that I'm now doing 16-bit comparisons instead of 24-bit. Now the rest of the code, it's all exactly the same thing. I'm basically just doing 16-bit everything all the way through. The whole thing is a lot shorter than it was before, and it's going to be a lot faster. So let's run this and see how much better it's gotten. Now the first thing that I'm going to do is show ellipse 6, which is the code we had on the previous video just for generic ellipses, so that we've got something to compare with. And I'm doing this in MartyPC, which is an emulator, but this is cycle accurate, and it actually tries to modify the performance so that it exactly matches the speed of a 4.77 megahertz PC. And I've checked the performance metrics for the emulator, and it is actually running at the correct speed for my laptop. So what you see here is what you would see on an actual PC. And I've actually managed to update to MartyPC 0.2. Turns out there's an interesting story there. The author, GloriousCow, reached out to me after seeing some of my videos, and he'd noticed a few things and made some suggestions. And I was also able to pass on to him some of the issues that I was facing, and we managed to sort all of that out. And so now I have the latest version working brilliantly on my PC, and it's saving so much time. So thanks very much for that. So let's run this, and basically it just starts off drawing a circle and does a little animation of it. And this is the part that I wrote to do some timings. So it'll scroll through this 10 times, and each time it's going across here, it's drawing 200 circles. Now this wasn't very much faster than the previous version we had. I think it was less than 3%. I think this takes 32.5 seconds to go through 10 of these swipes. So keep in mind how this feels, and we'll do a comparison in a moment with the new code, and you can see whether it feels any faster at all. So the new code is circle 5, and it does the same animation. I think that felt a little faster. Let's see how we go here. And yeah, that definitely feels faster. So I actually have timed this, so to do 10 of these swipes, it now takes 22.5 seconds, so it's almost 50% faster. I don't know whether you can believe that. It was a pretty big surprise to me, but just changing from that 24-bit arithmetic down to 16-bit has made all of that difference. So success, I now think we've arrived at what should be the fastest possible code for drawing circles, at least if you don't go completely crazy. Now there's a few things that I probably should mention to finish off here. If you go through the calculations, you'll realize that we're now doing about 90 circles per second. And because the monitor is running at 60 Hertz, that means that we're taking about 2/3 of a frame to draw a circle. Or you could draw a slightly larger circle, and maybe it would take a whole frame. Now that's really great. It's really fast. If you go back to the early 80s and look at the code that was around then, you won't find anything quite as fast. And there's actually a good reason for this. Let's take a look at the size of the program that we ended up with. It's now at just over a kilobyte, and imagine that you had fast circle drawing code and fast ellipse drawing code. Well, that'd be 2 kilobytes worth. And at this point, I haven't even got to drawing arcs of ellipses or filled circles or anything like this. So if you actually do everything as fast as it can possibly go and write a new version of the code for everything, then you end up with really a huge amount of code. Now, back in the early 80s, a lot of the machines didn't have a huge amount of memory. In fact, the very early versions of the PC, I think, were sold in maybe even 16 kilobyte version. It didn't even have enough memory for a disk drive. You had to use a cassette player. Well, it turns out in practice everyone bought a diskette drive, but even still, the memory in the machine might have only been, say, 64 kilobytes. Or if you were writing ROM basic, then you had to fit all the basic routines into ROM. Now, I believe that many of the algorithms, perhaps even the circle drawing one, was not in the IBM basic ROM, and you had to use disk basic, but you might have still had this limitation of 64 kilobytes of system RAM. So this was a very real issue in the early 80s, and it's just something we don't have to worry about nowadays. Mostly we have 512 or 640K of memory in our machines, and we just don't care. But it really does make a difference if you're trying to pack everything into a disk basic or a ROM basic that is actually going to fit in memory. So bear that in mind and, well, enjoy. I really like writing code that's really fast and going back to this old hardware and pushing it in ways that you just wouldn't have done back in the day.